Okay, so this is part 3 of Unit 11B. The last video we ended with these symmetries of geometric figures and found these degrees of rotation for regular polygons. Again, regular polygons are where you have all sides of equal length. And in this case, we want to find out how many degrees can a regular n-gon, so a polygon with n sides, be rotated about its center so that it remains unchanged in appearance. And as we noticed up here, we took 360 degrees and divided by the number of sides to get that angle of rotation. So it's simply take 360 degrees and divide it by n, and that is the degrees of rotational symmetry. Rotational symmetry. And that's with, so I should say, with n sides. And then how many different angles answers the question, how many different angles answered this question for the n-gon? Notice that in our triangle, there were, oops, did not want to erase, wanted to highlight. In our triangle, there were 1, 2. Square, there was 1, 2, 3, 4. Pentagon, 1, 2, 3, 4. Or excuse me, there was 3 for the square, 4 for the pentagon. And so it turns out that there are n minus 1 different angles when you're dealing with, again, this is regular polygons where all the sides are of the same length. So it doesn't apply to every single polygon, but what we call regular polygons does apply. So the last little thing we're talking about is tilings, sometimes known as tessellations. So with those, they involve covering a flat area such as your floor with geometrical shapes. And tilings usually have a regular or some kind of symmetric pattern. And these things are found all over the place. If you look at different homes, different tile types, or tile types, I should say, that you have on the floor, they can come in all kinds of different patterns. They're found all over the place, and basically what you're doing when you're creating a tiling or tessellation, you're just covering up an area, a surface. So tiling is an arrangement of polygons that interlock perfectly without any overlap, so no overlapping. The simplest one, tilings use just one type of regular polygon. As you can see below there, I've got triangles, squares, and hexagons. And note that there are no gaps or overlaps between the polygons in these three cases. In each case, the tiling is made by translating or shifting the same basic polygon in different directions. That is, these all have translational symmetry. So you're just rotating them, or not rotating, but you're just moving them side to side and up and down. So what we're going to do is, here we have a figure, and you're not going to be required to, in this class at least, this lesson, you're not going to be required to draw out a tessellation, but it can be, pretty, if you like art, it can be a pretty interesting exercise to do. And when I have done tessellations in the past, usually what I do is I cut out, I pick my shape and I cut it out, and then from there I just kind of slide it around. So I guess if I was just doing a regular square, then I would I guess one that I made was a square, and then I cut out this piece right here and I stuck it on the end. So it's just a very basic type of figure. So I got a figure that looked something like this, and then I cut it out, and then I just basically traced it and then shifted it over, traced it again, shifted it over, traced it again. Then you can shift it down, trace that figure. Oops, that should go farther this way and this way. But hopefully you get the idea. You can just start moving it around. And so with this one, here is something, a figure, and you want to try and make a tiling for this quadrilateral. So you want to be able to cover a big surface. So what you would end up doing if you're trying to do this by hand is what I'd recommend doing is you would take this shape, kind of missed a little bit there, and you'd get one, and then notice I can't just slide it this way, so this one is going to need more than what we call translation symmetry. I'm actually going to be needing to rotate this around, so I need a flat side to match with a flat side, and so I don't think it's going to let me do this. Okay, so I thought it was going to let me rotate it, but I'm not going to be able to. But anyway, what I would need to do is I would need to rotate it on its side, and then you'll see if I could draw this thing so it goes something like this, so it matches up, and see if I can continue this until I start finding a pattern that covers it. And so here's generally what you come up with. So notice, you have one object right here, and then it's kind of rotated around, and then you have the next object here, and then you've got the same orientation just slid there, and then you've kind of reflected. Well, you've rotated on that one, and then here is the original again, and you just keep going, and this could fill up any size of area that you have. And this is the idea of a tessellation with using different translations. So you have rotation, you potentially could have a reflection, translations, and so forth. But in this lesson, what you're going to need to be able to do is, if you're given a certain figure, such as this here, so I'll erase all this right here. But if you're given, this figure, for example, you would need to be able to look at several different examples and determine if it can be a tessellation, meaning that it can be drawn and cover up a space without any overlap or any gaps, or not. Some of them it works well, others it's not possible, and again, you'll just have to visualize that. You will not have to actually go and draw these things again, because this is math, not drawing. So we're just looking at, can we cover a certain area with a shape using symmetry. So that ends 11b.